Continuing along with various causal mistakes in reasoning, we now turn to confusing conditional probabilities in medical tests. And this is something that's important when one gets medical tests. And before the pandemic, when I taught this, it was to most people fairly academic. But of course, the pandemic, when almost everyone was getting tested for COVID, this became rather significant. So here's how the reasoning goes, and an example of how it can, go badly. Now, what underlies this is the following thing. The probability that X given Y is distinct from the probability of Y given X. And people sometimes can assume that the probability that they have a medical condition is high if they either score high on a test for that condition, if it's got like a scale to it, or that they surely must have the medical condition if they test positive. And of course, people generally are aware of, positive, false and false negatives, etc. But what's interesting to look at is doing the math for this, which can be, in some ways, kind of reassuring in some cases. The practical kind of gist is that basically a positive test for something on the the positive side doesn't guarantee that one has that condition. So let's get into the number crunching, etc. So here's how it goes. Taking the example of medical test, if a person tests positive for a medical condition or any condition, and we could take, for example, a person gets a positive test for COVID, that is, of course, the effect of the condition and not the cause. So it's not that if one tests positive, then one must have, the cause, the condition. Rather, it's that if one has the condition, say one has COVID, then the effect would be that one tests positive. So how does this mean in terms of, again, practical number crunching, etc.? Well, let's take the example that the authors used. So imagine there's a test for bladder cancer that's 90% accurate. And 90% is, pretty good for medical test. It's, kind of a good standard. That means, of course, that 90% of people who have cancer, which is the cause of a positive result, will test positive, which will be the effect. The cause of testing positive is having cancer, assuming the test is working properly. So suppose someone tests positively for bladder cancer. Now, a person might leap to the conclusion that if a test is 90% accurate for bladder cancer, that if they test positive for cancer, then there's a 90% chance they have cancer, which would be, of course, terrifying. But this is not actually the case. So what is the actual mathematics? So to know the actual chance of having a condition, taking the example of cancer, you would need to know the percentage of false positives, how often does that occur, and the base rate of that condition. That is to say, the frequency of the cause. So this would require us knowing some things, which can be a problem if we have like something new, like when COVID came out, we were operating, in the dark in terms of we may have a kind of an estimate about how accurate the test is, but we wouldn't know the frequency of the cause, etc. But assume we know these things, something, say where the base rate is well established. So using the example from the book, suppose 10% of men who don't have bladder cancer will test positive, that the test is 9%, accurate, and has a, 10%, false positive rate, which is pretty good. And suppose the base rate in the population is 1%. Suppose we know this because of medical research. So out of 1,000 men, 10 of them, 1%, will have bladder cancer. Of these, since the test is 90% accurate, 9 of them will test positive. Of these 1,000 men, 990 will not have bladder cancer because the base rate is 1%. But since the test will give back false positives 10% of the time, that means of the 990 people who don't have bladder cancer, 99 of them will test positive. So out of a population, of 1,000 people tested, 108 people will test positive. But of these 108, only 9 of them will have cancer. So a person who tests positive does not have a 90% chance of having bladder cancer. Rather, they have an 8% chance of having bladder cancer, which of course is, from the standpoint of not having cancer, is much better. Now, again, this may seem kind of confusing because we naturally tend to think if a test is 90% accurate, that means that if you test positive, there's a 90% chance that you have it. But that's getting reversed. The actual thing is that it's not if you test positive, there's a 90% chance you have it. It's that if you have that condition, there's a 90% chance that you will test positive, which means there's a 10% chance that a person will test positive who, doesn't have that condition. And of course, there's also the possibility of false negatives. And this kind of bad reasoning can be made, not just in medical cases, but any time that there's a test for something. Because even if a test is, highly accurate, if it's less than 100%, then obviously the mere fact that someone tests positive or the test is positive doesn't guarantee that the cause is present. So that's confusing conditional probability in medical test. Now, the inference is not to take medical testing seriously, but a thing that can kind of help address stress is that even if somebody tests positive or something, this is why it'd be important to get tested again, because it may turn out to have been a false positive. Because if a test is not 100% accurate, false positives will also obviously be possible. Another common mistake in causal reasoning is what's called overlooking statistical regression, sometimes known as regression to the mean. The statistical regression and regression to the mean refer to statistical measurements of mean values in populations, not mean in the sense of that they're cruel, but in the sense that, going back to earlier parts of the course, the mean value is again the average value. Now, what happens statistically for various reasons is that measuring large populations tend to regress to the mean. For example, in the short term, we can get very seemingly unusual results, but of course the idea is that if we keep kind of repeating the examination of the statistics, that will soon regress back to the mean. So take, for example, guessing on a true-false test. Now, if you gave people, a true-false test that was, say, impossibly difficult for them, and they just guessed on it, suppose it's some sort of, terrible psychological experiment, some people will score just by guessing above 50%, and some will score below. But the average will be about 50%. Now, you'll of course expect to find people who score above 50%, just, by random chance. But we wouldn't infer that the people who happen to score better than 50% have some sort of special, test-taking, ability that even when they don't know the answers, they can somehow get them right. And we could easily test this by having the people who got, say above 60%, give them, keep giving them true-false tests. And eventually, what we'd expect to happen is the average would be closer to 50%. And so it's not surprising that people, in such a case would be different from the average, but of course we would expect it to regress to the mean. Another example, athletes, like in sports, what will often happen is that an athlete might start performing above their average in a game or a season, and then what will typically happen is that they won't repeat that, say, the next game or next season. Now, you'll often hear sportscasters talk about the person is losing concentration, because they're, due to their success, or that other athletes started focusing on them, or there was a coaching change. And they talk about someone being like on fire, but then they're not on fire anymore. And those things could be possible. Those could be true, but it might also just be statistical regression. That it is not surprising that a person would perform above average in a game. I mean, or in a season, just because of random, chance, etc. And if they go back to their average, well, that's in a way kind of to be expected. Now, regression to the mean can happen whenever a phenomena like the ones like athletes, etc., the other ones, someone guessing on a test, occur. Once it's one takeaway is, of course, that you shouldn't go by the results of, say, one consideration, like one game performance or one season's performance, or a person, their performance on one true-false test where they guessed, because one or even just a couple samples won't capture this adequately, because it may just simply regress back to the mean. So again, if someone claims to be like really good at guessing sports teams, and when they guess, they might do better than average, and then you keep testing them. So the next time you'd expect them soon to go regress back to the mean. Now, of course, if it doesn't regress back to the mean, with a test after test after test, then it's reasonable to look at it and consider maybe there is something occurring there. So using a hypothetical case, if there was someone, if you gave them any true-false test, regardless of the content, they could always guess at least 60%, and they did this over and over and over and over again, and you found no other way to explain it, like cheating, or they actually know a lot of stuff, then you might begin to suspect some sort of strange phenomena in place. In that case, that'd be worth considering, but probably unlikely. So we'd always want to consider that even though something may seem like out of the average, that this may be exactly what you'd expect, and it could regress if one goes and checks it again. So that should be properly considered. Next, the proof by absence of disproof. Now, this is something we looked at earlier when we talked about the appeal to ignorance, and the idea is this. It's sometimes claimed that the absence of disproof for a causal hypothesis increases the likelihood that the hypothesis is true. That is to say, that there's not evidence against it, that it counts as evidence for it. So a person might say, no one has proven that drinking tea with honey in it does not cure colds, so perhaps it does. Or someone might say, no one has absolutely proven that vaccines don't cause autism, so maybe they do. Now, the mere fact that there's, even if someone claims that there's not absolute disproof, is not proof of something. And the reason why is that the failure to disprove a causal claim only leaves intact whatever reasons you had initially to think the hypothesis is true. The mere fact that one is not pointing to evidence that goes against it doesn't give you a reason to think that it's true. So if there's no evidence for something, then saying, well, there's no evidence against it doesn't prove it. I mean, to use a kind of weird example, think of like UFOs. Or rather, supposedly those exist now. So we'll go to like ghost. And suppose someone says, well, no one has proven that ghosts don't exist, therefore they do. Obviously bad reasoning. I mean, one could just take any kind of fanciful creature. You'd say, well, no one has proved that invisible unicorns that don't show up on infrared and you cannot hear them, that are absolutely silent, no one's proved that they don't exist. But obviously that's bad logic. So the mere fact that there's not conclusive disproof of something doesn't prove that it's true. Doesn't prove that it's false, but doesn't prove that it's true. Our next fallacy is one we saw earlier, the appeal to anecdote or appeal to anecdotal evidence, or sometimes called anecdotal evidence. And this hasn't changed since we looked at it earlier, but to recap it, in the context of causal reasoning, this is a fallacy that occurs in the context of statistical reasoning, in which data that offers reasonable support for a general claim are ignored in favor of an example, a story, or two that do not. So when talking about causation, the fallacy occurs when someone tries to prove or disprove that one thing is a causal factor for another by citing an example or two that didn't or did cause that alleged effect. For example, if someone says, hey, red wine prevents colds. My friend Bill, he drinks red wine with every meal, and Bill never gets a cold. Now, of course, that's bad logic, because the mere fact that even if it's true that Bill never gets a cold, then the mere fact that Bill drinks red wine, doesn't get cold, doesn't prove that's the cause. There's obviously no statistical evidence that shows that it's a prevention for cold. Now, also, of course, saying that red wine doesn't prevent colds. So if someone replies back, it says, suppose I say, my friend Bill drinks red wine with every meal, he never gets a cold, so it must prevent colds. And someone says, well, that's not true. I drink red wine and I still get a cold, so it can't prevent colds. That would also be appeal to anecdote, denying that it does prevent colds. Again, the only way to reasonably determine if red wine is a preventative effect is not look at one person who drinks it and say, aha, they drink it so they don't get colds, so it prevents colds, or saying, well, when this other person drinks it, they get cold, so it doesn't have any effect on colds. It would both be this fallacy. Again, you would need to have, to establish as a causal factor, you need to use either the experiment or studies that we looked at in the case of causal reasoning. So simply giving an example or two in which something occurs or doesn't occur doesn't prove or disprove a causal connection. Now, isolated incidents, especially if they're kind of unusual, could raise suspicions about causal factors. So if, people, kind of notice like a few anecdotes about people eating yogurt and say having healthier, better digestion, for example, or less gastrointestinal ills, then it may be worth looking into and say, well, maybe there's a factor here. But of course, we need to run, appropriate studies and experiments, etc., to test it out. And so anecdotes can be interesting and can lead to further investigation, but by themselves they prove or disprove nothing, because they're just anecdotes. Next bit of bad causal reasoning is not really like an error in causal reasoning, but a different type of mistake. And this is confusing explanations with excuses, or worse, justifications. So there are cases when someone can engage in an explanation to explain in order to make an excuse, or even justify something. Because an excuse is essentially saying not that it was something, basically that one is not to blame. And justification is often typically used, not always of course, but typically used to say that something that may seemingly be perhaps bad is actually, if not good, at least, warranted. So why is it important to avoid confusing explanations with excuses? Well, the mistake is this occurs when a person assumes, without justification, that someone else trying to explain something, typically like, bad behavior, is therefore trying to excuse it or even justify it. Because a person can, of course, explain something without approving or disapproving of something, and a person might actually explain something and really disapprove of the action. They're not trying to say that it's justified or excused. They're just trying to say this is why this occurred. So, for example, this occurred quite a bit after 9/11, because this is kind of getting to be old history now. It was obviously 2001, so quite a while ago, but still, of course, a very vivid event in American history. So after that occurred, there were attempts to explain it. And some people explained it not in terms of sort of the accepted, ideology of the time, which was that America is being attacked because people hate our freedoms, people are offering explanations in terms of, say, a past American foreign policy, that the United States was being attacked by terrorists, not because they'd said, hey, we really hate America's freedom, let's go attack America, but because of what America, the United States, had done in the past in terms of what the United States had done in the Middle East. And some of the people making those explanations were attacked, and on what was alleged was that by explaining it that way, that the attacks were caused by a response to American foreign policy, the assumption was that these people must be trying to justify the attack. And in some cases people might be, but the credible sort of researchers and academics who looked at this, people who look at foreign policy, said, no, we're not trying to say that it's justified, but we're saying this is the explanation. It's not that people said we hate America's freedoms, we're going to go and attack America. The explanation was American foreign policy in the Middle East, at least in part. And so the person was not trying to say people are making this claim. We're generally not trying to say it's justified, but this is the explanation. And so we have to watch for, especially in politically charged things, that a person can explain something without justifying it. As a more recent example, consider the Russian invasion of Ukraine. Now, a historian might explain this in terms of, say, that going back to my own political science classes long ago, my political science professor said much of what Russia historically has done is try to get a buffer zone between itself and typically Germany, but also obviously France and England, because the French under Napoleon invaded Russia. The Germans also in World War I and World War II attacked Russia, or then in World War II the Soviet Union. And so one could say that one explanation as to why Russia tries to expand is in order to create a buffer zone between itself and what it considers, say, traditional enemies, Germany, France, etc. Now, in this case, that explanation is not trying to justify Russian, invasions, not saying that they are right and good for doing this. It's simply providing one political explanation as to why that's done. Why do the Russians do this? One possible explanation historically has been to create a buffer between themselves and Germany and France. Now, this explanation could be untrue, but it need not be an attempt to justify it. Now, of course, people can attempt to justify things by explaining them. So if someone were to say that Russia, expanded into Ukraine and invaded it in order to protect itself from European aggression, and this was something that was good, that would be an attempt to justify it. And so the way you sort it out is to look at, is a person simply saying, this is how or why it occurred, or are they adding in sort of a normative element, saying that this is how or why it occurred, and this is therefore something that is, if not good, at least warranted. And so we'd want to watch for that distinction, especially in the case of things that are very ideologically charged and very, very emotional, like trying to explain things like terrorism, for example, or wars. So that brings us to the end of looking at some of the causal fallacies, and the next video will finish up part 3 of the course, looking at causation in the law.